Hello. Let's start lecture one by mentioning the first chapter that we're going to talk about is chapter 11. If you notice, this is the same book that we followed from statics. Therefore, the chapters behind or previous to chapter 11 are basic concepts for statics. But also you have vectors and how to deal with vectors. So go ahead and review those in case you don't remember how we do operations with vectors. I'll post a review, but make sure that you know how to find that type of material in this book. So chapter 11 is the kinematics of a particle, which we're going to learn what that means, and then we're going to use those concepts to move and study systems. So one thing to consider is that this chapter goes from linear or rectilinear motion of particles. That does not mean necessarily that it's just a straight line, but it means that it's only one dimension, two if you consider time. So, for instance, if we have a particle that moves freely, this is not going to be xy. This rectilinear means that is going to be time and distance. Time in the x-axis, distance in the vertical axis. So this means basically that if you have a map and say you have San Antonio, then this means that the distance covered was, let me fix this, draw, go back to draw. Okay, so let's say we had 0, this is O, reference frame is O, 0, 1, 2, 3, 4. And got it. And let's draw this one a little better. Okay. 1, 2, 3. All right, that's 3. So what that means is the first second, you traveled, this is in meters, this is in seconds. Could be milliseconds, could be nanoseconds. But let's say in 1 second you traveled 1 meter. 1 second, 1 meter. And 2 seconds you only traveled 1.25 meters, let's say. In 3 seconds you traveled around 2.5 meters. Let's do that again. In 3 seconds it's 2.5 meters, and in 3 seconds is, sorry, in 4 seconds we traveled 2.8 meters. Okay, I'm just approximating here based on the draw that I made, the graphic that I made, plot that I draw. Okay, so that means that again, let's say we're downtown San Antonio. Actually, let's make this kilometers, or yeah, so kilometers. This means is 1 kilometer is 1,000 meters, right? You remember this. This is 1 kilometer, and you know how many miles that is because 1 mile is 1.6 kilometers. So this is about 600 miles. All right, so this is 1K, okay, 2.8 kilometers. It's quite a lot actually. So it's a lot of distance. Wow, that's a lot of distance in very few seconds. That is, yeah, that is like, well, that is not very doable because I don't know what system will be able to do this because the speed of light is around 300 kilometers per second, but I don't know. This has to be a very, 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 very fast jet or something. But anyway, regardless of what system can do that, an Omni or some alien ship, whatever, um, we have from San Antonio in 1 second, we moved 1 kilometer in some direction. North could be 1 kilometer. I'm trying to type 1 kilometer, I'm not able to. 1 kilometer, okay. Perfect. Then in 2 seconds, so it's 1 is right here, 2 seconds is right here. This distance from here to here is 1.25 kilometers, so 1250 meters, 1.25 kilometers. That means that there was the some variance in the acceleration. It's not a constant speed, because if this was linear, let's use a different color. If this was linear, then it would have been in 1, then in 2 would be the same amount of, say, 2 kilometers could have been, but no, it's not a linear function. So as you can see, the concept of rectilinear just means that it's one dimension and in time. So it's a function of one dimension in space and time. Usually time is always first, so the proper way of expressing this is like that, as a function of time and distance. And this guy could be expressed mathematically as some type of cubic function. I don't really know, it doesn't matter right now. But the point is that this is a rectilinear function. So we're going to start by dealing with these type of functions. Okay. All right. So going back to what we're going to go for. So under rectilinear motion, we're going to learn how position, which is the x variable that I was mentioning about, velocity and acceleration. By now we know that velocity is the derivative of position and acceleration is the derivative of velocity. We're going to determine the motion. So this is with respect to the coordinate system. We're going to mention some special cases. Then we're going to talk about very simple case, which is uniform rectilinear motion. This is the simplest case you'll ever see. And then accelerated rectilinear motion, so it's the function that I just showed. Then motion of several particles, how to interact between several particles that create a system. Then we're gonna go over some concepts of how to graphically come up with solutions. It's just by determining the area under the curve of the acceleration, you get the velocity. It's just very simple stuff. Now we're gonna talk about the curvilinear motion, which is not as easy, because now we're not so used to seeing this type of systems, and we can sometimes use polar coordinates, which we might have to review. And then of course we're going to do the same mapping of finding the position, the velocity, and the acceleration in that curvilinear motion, finding the velocities, and comparing to rectangular, which is the x and y. This is the rectangular coordinate system. Where is my rectangular coordinate system? Yes, this is rectangular because it's 90 degrees between my axis. Polar, if you remember, we're gonna have an r of radius, a distance, and an angle. So it's very convenient for rectilinear, I mean for curvilinear problems. Um, and then finally, we're gonna learn the tangential and normal components, or as the radial and transverse. So you're gonna see how they're related. So chapter 11 is a very important chapter in this class. So we're gonna go over a lot of examples and always go back to compare to what we know as the concepts.